So let me just give a brief introduction of what I've done during my PhD thesis. Actually, I'm worked with the hardware that Adrian and Theo were working with from the Bluetooth cluster. So let me just introduce a little bit the background. So in this work, I'm considering two physical applications that are related to fluid dynamics. The first one is called bluff body flows. And basically, it's involving an object that is traveling into a fluid, and the fluid has some viscosity, so it's opposing some forces. And the ratio between the inertial forces of the object that it is exerting on the fluid over the dissipation forces, it's like the most important number to quantify the complexity of the problem. Another, and this actually is a picture taken in the 96. It's an experiment where you have exactly the cylinder moving in this direction, and this is the nice patterns that is generating, and actually is identifying the vertical structure that you might have. And you can see that basically you have a lot of different scales. The temporal scales, unfortunately, you cannot see them, but the spatial scales, you can see them. They develop very fine vorticity lines here, and everything starts from the boundary. So basically, it means that the boundary is generating some new scales, and those scales have to be because they are so fine, if you want to simulate such phenomena, should track with very high resolution all the vorticity in the field. The next application that was focusing on is called shock bubble interaction. So in this case, we are not assuming an incompressible flows. We should consider the full Navier-Stokes equation where we have compressibility effects. Indeed, in this case, we consider an argon bubble inside air, and in the air, we have a shock in the density, and we shoot the shock against the bubble deforms. In this case, the dissipation forces are negligible compared to inertial forces, and this leads to a completely different discretization. So also in this case, you can see that from experiments done at Caltech in the 92, you can see how basically the simple form can generate more complex patterns. And also here you can detect the presence of small scales that actually determine the behavior of the coarse scales. So to summarize, if we take just these two examples, we can see that there is a generation of a set of scales, okay, that are in space and time. So this might lead or can be generated from the wall boundaries or between the interface between two fluids or two phases. In any case, these simulations are dealing with small-scale generation. And this is very, very expensive in terms of simulations, because basically it means that you have to increase your resolution. Not only in time, not only in space, but also in time. Basically, for every small scale in space, you can somehow relate what's the dynamics of that scale in time, and therefore you have to spend a lot of integration steps in your simulation. Now, this concept or this issue is not present only in fluid dynamics application. It might be found also in some other biological applications. Like here, we can see an extracellular matrix generation, and actually it's about creation of vessels done by other colleagues in my group. And also here you see some angiogenesis. In any case, what we wanted to do was to efficiently solve this small-scale generation by providing some algorithmic improvements by focusing the computation only where we actually needed the high resolution, and also port those expensive parts of the solver into two GPUs or at least two SIMD engines. So for the algorithmic part, we use wavelets. So wavelets can give some very nice advantages over other discretization types or other techniques, because actually they give a consistency between the scales, and with wavelets it's easy to describe the same problem at different resolutions. As you can see here, basically the powerful tool of the wavelets is provided by the multi-resolution analysis. This means that the same information can be represented in a different resolution level, where we have the coarse one, the coarsest one, and the finest one. Now, how can we switch between one resolution and the other in some region of the image? Well, this is done with a forward wavelet transform, where essentially we apply an analysis step where we want to get rid of negligible information in order to fill up the next coarse level. So in this case, we take a signal, we decompose into two different signals. One is called details, because they are details, so they are supposed to be the ones that are negligible. And the other one is called the scaling, which is the information that we are further processed to generate coarse representation of the signal. Now we can also do the inverse step. So given a coarse representation and some detail, we can generate the finest scale. So this consistency between going to high resolution and low resolution, it's a very good discretization point that we can apply on the physics that we are simulating to switch resolution. Now, based on wavelet, we can actually generate some grids. And this is done with the thresholding of the forward wavelet transform. So basically, by having this notation here, where we threshold all the negligible details, we can end up with two different types of grid. Here I'm illustrating just a two-dimensional case. So it's the wavelets can generate two different types of grids. The first one is called vertex-centered. As you can see, all the degrees of freedom of the grid are placed in the vertices. The other one is called self-centered. It's not up to us to choose which type of grid we have to choose. It's given from the wavelet. You choose the wavelet gives you either vertex-centered grids or self-centered grids. Now let's solve a PDE. So let's perform a simulation on this grid. It could be very difficult if we just consider the grid points independently. But what we can do through the wavelet transform is we can convert this PDE here, especially this differential operator here, into Gauss reconstructions. Basically, through the inverse wavelet transform, we are able to generate auxiliary points to create a local uniform frame. And then once we have a local uniform frame around the grid point, we can easily estimate the differential operator on that point. So if we want to use this technology or this set of algorithms that are wavelet-based inside a simulation, we also need to keep the grid adapted to where the dynamics are. This means that we have to come up with a method to do this automatically. So what we do is the following. So we have an adapted grid, and the first thing that we are going to do is to refine everywhere the grid. That's because we don't know where the new scales are going to emerge. Then we are going to compute on the grid, so the grid is going to stay fixed. The structure of the grid does not change in this step. We're just evaluating the differential operation. We are solving our equations. And then we perform a compression by performing a forward wavelet analysis. And there we can get rid of the points that we were creating here that were not really necessary. In this way, we can perform simulation steps very nicely. Now, this step here and this step here, you try to minimize the cost because that's the overhead that you have to maintain the grid adapted. So what you want to do is that basically this step here and this step here take overall less than 10% of your total time. And inside the computing step, the first thing to do is to reconstruct the Gauss, and then we have a very expensive evaluation in terms of arithmetic operations, and then we are going to update the solution. So I'm going to discuss this now. So another way to accelerate the process or the discretization that is wavelet-based for multi-core and GPUs is by introducing blocks. So if we just perform the wavelet analysis on every individual grid points, then it might be too expensive, and also, although it's data parallel and it's fine-grained, it's not homogeneous because it depends very much on the grid structure around those points. So what we want to do for multi-core and many-core, we want to regularize the tree structure that is behind the wavelets. So we introduce blocks. So this is just to guarantee some regularization inside the computational elements to have fast access. So what we did for GPU acceleration was just to take the computing step. So as we saw, the computing step was consisting of three individual substeps. The first one is to reconstruct the ghost. The ghosts are kind of difficult to reconstruct, or more than difficult, they are irregular, so they don't map very well on the GPU. Then once the ghosts are reconstructed, we can evaluate the red inside, and this is very parallel, very homogeneous as well. So we can port this to the GPU and then perform an integration step on the CPU. So we perform the integration step on the CPU because its performance is bounded by the memory bandwidth and not the compute power. So in essence, let's say we're performing an Euler type of time integration. What we do is the following. So this is the new state of the simulation. This is the old one. This is the evolution part, so the part that we have to compute in order to evolve the simulation. What we do, we delegate this to many-core computing. So what we did was we developed a framework that is based on OpenCL, and it's completely asynchronous. On the left side, you can see the CPU. Actually, this is a data flow. The CPU is basically responsible for maintaining the wavelet blocks that contains the actual information. And then even still on the CPU, we reconstruct the ghosts that you can see here around every block, and we pack blocks all together so that we have a lot of parallel work items that are fine-grained and homogeneous that are ready to be sent to a GPU array. And then once the GPU are done, we receive some other packs of blocks containing the right-hand side, so the term that we need to evolve the simulation, right? And then this is done again on the CPU by mapping or finding the individual entries in this block packed and updating the blocks. So I need to mention that everything here is asynchronous. So this is done with some task-based parallelism that is non-blocking, while this part here is performed with OpenCL in an asynchronous fashion, and also this one here. So if we look inside one GPU, what we do is a rather complex processing type, because the dependency between the different kernels is non-trivial. It's not like a chain, okay? So the first thing that we need to do is we need to reconstruct like the information at the cell boundaries, and this is kind of expensive. So for every point in the wavelet grid, we need to reconstruct those informations. And this generates a lot of intermediate data that then is further processed in order to evaluate the flux. And then once the flux is done, we can sum up the intermediate data and produce what we need to in order to update the simulation. So as you can see here, we have we can identify at least 3 steps, where the first step is involving 4 kernels calls, and the second one is involving 2 kernels calls, and the last one is involving 1 kernel call. So this dependency is very difficult to express in terms of synchronization points. However, OpenCL provides this concept of events that in this case can be extremely useful to describe the complete dependency of this processing. So this is one, I'm just showing some simulation that we performed just to show what actually we are doing. So we are simulating with this spatially varying grids, and we have also proved the accuracy, which was able to be the state-of-the-art results. And also, we managed to have some flexibility in the solver in order to allow complex geometries. And here, as you can see, basically, the vorticity generation, it's led by the boundary, and is tracked through the wavelet transform. And the block, you can follow the block, you can see the blocks following the vorticity course. Of course, especially in industry, one thing that is desired is the handling of multi-object simulations, and this is easily done, of course, with some software engineering on top of our solver. And another thing that is very important in industry is some 3D applications, so you can apply the same technique for three-dimensional problems. Now, I have to mention we didn't just use GPUs, because we think the difference between the GPU and the CPU, if your CPU program is efficiently written, cannot be higher than 8x. So in this case, we just used CPU. In this particular example, I wanted just to show you the performance of the CPU. Here we are considering Brutus node, an AMD Opteron at 2.5 gigahertz with a nominal performance, peak performance of 320 gigaflops. And we could reach, so we had to solve a Poisson problem. And this, the way it's done, the implementation is able to reach approximately 180 gigaflops, which means that we are able to reach like 55% of the nominal peak performance. And this was without counting the intrinsics that we use to shuffle operations and to perform logical operations. And so what we wrote for the CPU part, it looks always with something like this. So basically, it's not even C++ anymore. It's like just full intrinsics. We use some of the techniques of C++ to generate better code. In this case here, I'm using template specialization to choose the implementation. Now, this is done on the GPU. This is done actually with 3 GPUs, 3 T10 Teslas, the first generation, and it's a shock bubble interaction. And yeah, here you cannot really see the difference between the resolution because the wavelets are high order. Now I can show you the grid. So you can see that the shock is tracked exactly where we need to put computational elements. There we get refinement. And therefore, this basically, by not refining the region that are not interesting, we gain some performance. We also checked the accuracy of this compared to state-of-the-art results collected abroad. And also we compared with what we consider to be the reference framework or the reference software for these particular applications, which is called Chombo. It's coming from the Lawrence Livermore National Laboratory, and it was also in collaboration of the Para Lab, which is one of the highest reputation group in the University of Berkeley. So Chombo, in this case, has a slight different discretization. So it's actually not able to do single-phase problems. So there we cannot really treat the bubble as a helium. We have everything is treated as air. It's just the density that is different. And it's second order in the accuracy in space. Our solver is multi-phase. So it's not really fair to compare the same thing. But in any case, also the accuracy was higher. In our case, it was fifth order. So what it turns out is that our solver for this specific case was like 2 times faster than the reference solution, than Chombo, for CPU. So I think they did also a nice job for the CPU part. But then when we turn on the GPU, actually from 56 minutes, we go down to 7 minutes. And this is almost one, actually is more than one order of magnitude difference in performance. So we performed also some strong scaling study. Here you can see actually the performance of the evaluation of the right-hand side, so the part that has been ported to the GPU execution. Here you can see the number of cores. We just used the machine that Adrian was discussing earlier. So we used 12 core machines up to 6 GPUs. You can see that already by using one, we have a massive speed up of 80 actually. And then by using 2 or 3, we reach a speed up of 100. This is by using more than one GPU. Of course, by increasing more than 3 GPUs, we have some issues also because we cannot hide data transfer anymore so efficiently. So, but I have to mention that theoretically, if you just see the specification from your hardware, the performance difference between this machine, this 12-core machine, and 1 Tesla couldn't be more than 10x. Okay, so it means that we did a better job. Somehow we are better in writing the GPU code than writing the CPU code. And I think that's the point of GPUs. So just as a summary, if we just consider the overall acceleration gains, not only the part that has been ported to the right-hand side, we see different improvements. So the main improvements, of course, is the algorithmic one. So if we are smart in discretizing our equation, if we are smart in choosing the algorithm, then we get the main advantage out of it. And that was, in our case, 24x. Then, because we vectorized the code, we were able to accelerate the time to solution to an addition of 1.8x. And then, because we used the work stealing approach to balance our computation, we managed to have 12x out of 16 cores. And on top of that, we have 3x for the GPU acceleration. Here, so that's overall, it's approximately 3 orders of magnitude improvements for time to solution. So what we are focusing now, it's actually combining AVX with OpenCL for re-entry studies. So studies of objects that are re-entering in the atmosphere. Here you can see a supersonic flow around the torus. Just a torus is a toy example for more complex geometries. So my conclusion is that GPUs can provide an important gain in terms of performance. So if you just compare micro benchmarks, you can easily see that there are performance difference that ranges between 2 and 7x. One GPU versus one multi-core solution. But one problem of GPUs is that although they provide this high performance gain, the performance is very fragile. You don't pay attention to a detail, you lose everything. And it's like the bad side of GPUs. And another side is the aggregate bandwidth. So if you take into account not only the internal bandwidth of the GPU, which is very high, but also the PCI Express, so the fact that you need to pass through the PCI Express, then it's really hard, it's really difficult to get any benefit out of the GPU. So the thing was solved here was with some overlapping between computation and transfer. And what NVIDIA is suggesting, if you look at the optimization guide and the best practice guide, is to move everything to the GPU. And in my opinion, it's not really something reasonable. Also because, let's say in 5 years, you have a new platform, slightly different, then you have to move again everything to the new platform, right? So what we're really looking for is some sort of heterogeneous computing, maybe some co-processors that are close enough to the CPU so that there is a collaboration, so that you just focus on the very expensive part of your code, and you don't need to move everything on the GPU just because of the PCI Express. So the GPU execution imposes also some rigid requirements. So let's say you come up with a very smart algorithm. If it's smart, it means to some extent the algorithm is going to be irregular. Irregular, it's okay if you program it in Java or in C++, but if you port it to a CPU, to a GPU, probably you would see some lacking of performance. So what I've learned in this work was that before porting anything to the GPU, you should apply a relaxation process where you trade off some of the algorithm improvement with some regularization of the problem, okay? So like a trade-off like the wavelet blocks that we've done here. And of course, another way to take advantage of GPUs for smart algorithm is to combine heterogeneous computing. So you delegate the complex part of the algorithm to the CPU or to some sequential compute unit, and the costly one to the GPU. So it's a cooperation. And actually, because we're really believing in this step here, I have to mention, so this simulation here was done on an APU. I don't know if you know APU, these accelerated processing units from AMD. So basically, they removed the GPU. They put the GPU on the same chip of the CPU, and the GPU is fetching the same DRAM bytes of the CPU. So I think this is really like a next step into the future. Okay, I think, yes, that's it. Thank you for your time.